So first, I'd like to introduce Dr. Rod Mackie. He is from the University of Illinois. And Rod, we decided we'd go very short on the bios so that we could have plenty more time for questions. But he is a very distinguished anaerobic microbiologist. And I spend a lot of my time emailing Rod, but it's not about microbiology. It's normally about rugby and who's beaten who when it comes to South Africa versus Ireland or versus New Zealand. Woo! Get off the stage. All right, welcome, Rod.
All right, so I'm very happy to be here and to share some of my insights into the story about methane and its potential for mitigation. So I put together a short slide set, and it's really quite obvious that people are only talking about methane, and it's not really about methane in terms of microbiology. It's about who's producing hydrogen and who's utilizing it. And the difference between utilization and production, that's the concentration. But it doesn't tell you what's actually happening in terms of hydrogen dynamics and hydrogen turnover. So to try and explain the point, I have this little demonstration here of the ratchet that's driving the whole process. And this is the reason why we need to have places that sink hydrogen. So in the process of fermentation in the rumen, anaerobic fermentations, there's a predominant pathway that's a glycolytic pathway, and it leads down to the central common intermediate, pyruvate, and in the process, you're producing reduced equivalents, NADH. And if these NADH and that redox balance changes, there's a problem. And so to make this whole ratchet work and turn, we need to dispose of those electrons. And we do that mainly in the rumen by using hydrogen to reduce CO2 and make methane. We also make other electron sink products, and these are things like butyrate, propionate, but also other intermediates, things like lactate and ethanol, that are probably short-term hydrogen storage things and turnover. And then intermediates like succinate. And so in terms of the general picture here, this is the situation that forage diets, cow-calf operations, there's less propionate, higher hydrogen and methane concentrations. And the important parameter to think about is the steady state dissolved hydrogen concentration. And those are things that people don't think about. But one of the complications of working with hydrogen is it's very, very poorly soluble. And that's part of the problem. So that it's very easy to accumulate hydrogen and start exhaling it. And anything that's being exhaled as hydrogen, that's a loss. That's a lot of energy disappearing out in breath. Okay, so where do electrons go during fermentation? And this is like a compilation of the paper that Sinead and the group in New Zealand and I with Tim McAllister worked on. And so the pathway or most of the electrons, 2/3 of them, are used to reduce CO2, make methane. So this is the predominant pathway. The other third probably come from things like propionate and butyrate. So propionate is a net, and then butyrate from pyruvate are sink products. Succinate, lactate, ethanol, they minor. We don't normally include them in a balance because they turn over, they disappear. But any accumulation, that'll have to be included in your balance. All of the other electron acceptors in the rumen system are really minor. Things like nitrate, sulfate, people have talked about those other organics, things like fumate and malate, are really substrate limited or toxic. Things like nitrate or sulfate make things like nitrite and things like sulfide. So the one that people like to suggest as an alternative competitor to methanogenesis is acetogenesis, but that process is just not competitive at all, although there's maybe some potential if we have elevated dissolved hydrogen concentrations that maybe this is an alternative zinc product. Unsaturated fatty acids or saturation of these unsaturated fatty acids is really a minor part of electron disposal. Probably one of the things that's greatly overlooked is the role of ciliate protozoa, and they have hydrogenosomes, these subcellular organelles that are primitive mitochondria that generate hydrogen, and they result in these epibiotic populations of methanogens. And they account for maybe about 20% of the methane comes from hydrogen that's produced by ciliate protozoa. And that's one of the big differences between a rumen population and other populations, hindgut populations. One of the other things I didn't mention up front is that we need to include formate in this whole story of hydrogen. And so formate is a nice soluble form of hydrogen. Okay, so what we did was got together, thought about this whole project, produced a number of publications, and it was really this idea of hydrogen production and hydrogen utilization. And that's what we used to convert into a proposal. So the Greener Cattle Initiative was put up by the FFAR group. We were successful in obtaining funding, and so that's about a total of about 3.2 million, which sounds like a lot of money, but it's not when it's divided amongst 6 or 8 different labs. So the Research Hub comprises these different centers. I don't really have time to go through them, but they include people from Illinois, Ag Research New Zealand, Canada, a European hub, but now Phil Pope has gone back to his homeland, Australia, Itzik Mizrahi in Israel, and then a commercial group, ProAgni, who are interested in the cetogenesis angle on that. So this would be a typical type of workflow for people that are working with animals. So out of those different research hubs, 2 are beef focused, 2 are dairy focused, and this would be like a typical type workflow where you use bioreactor studies, use those to titrate levels of dissolved hydrogen and fluxes of hydrogen formate in those sorts of systems, and then translate that into beef and dairy type cattle studies using methane inhibitors, and again, trying to correlate turnovers, fluxes with what's going on in terms of animal performance. And then the third part would be the synthesis, evaluation, and publication. So I think that really what we want to do is not change the system immediately, but provide a mechanistic understanding that will enable people to go on and make reasonable advances in the field. We're using state-of-the-art technologies to do sort of advanced bioinformatic, proteomic type approaches, and of course then to deliver those through different media channels. So what I've told you today is what people are really talking about in the meeting. So why methane? So that's why we're here. So short half-life buys time. What's the ruminal mechanism for methane formation? It's about hydrogen formation and hydrogen utilization. Work in my own lab looks at interspecies hydrogen transfer, one of the most intimate mechanisms for carrying out this process. And that's here. And then what are we planning to do? I've told you, I've given you an outline of what's going on in the Greener Cattle Initiative. I haven't described what's going on in each of the labs. But we also have a genetics toolkit proposal, which I'm not going to talk about. That's through the Global Methane Hub. And there's a couple of other Global Methane Hub proposals that are in the pipeline. And I wanted to end up with this slide. And if you don't remember anything about anything I've said today, just remember this picture here. And I decided not to use a Civil War type analogy, but this is the Battle of Waterloo. And so this is Wellington's troops on this side. This is Napoleon down there. So it's about capturing this hydrogen flag. And if we can redirect this hydrogen and get better animal performance, it would be a win-win situation. But at the moment, it's methane and concentrate diets over here. It's forage and high methane emissions down there. So the battle's being won by methanogens. So they're really, really good at what they do. And it's a long, long history of evolution between the animal and its host microbiome to make this happen. So that's my 10 cents worth.